Hello there. Good morning, good afternoon, good evening, and if you can't sleep, good midnight. So, today I'm just going to be sharing with you on how I did a project that uses logistic regression to predict if a person has breast cancer or not. So, it's just a simple project and it shouldn't take too long. So, the project just helps us to determine by different factors and different numbers probably that are derived through scans and different things, whether a person has breast cancer or if the person doesn't have breast cancer. So it's just a quick project and let's get right into it. So, logistic regression helps us with the classification problems where your usual linear regression can't help. So, for example, if we have something like this, just gonna choose the pen right here. So if we have something like this, I'm just trying to use the or show the linear regression problem, for example. So let us say I have the amount of fuel that's in my car. So let's say that's fuel, and let's just say this is the distance that I can cover, right? So let's say this is in kilometers. So the more my fuel is going to be, let's say 1 liter, 2 liters, 3 liters, 4 liters. Let's say 10 kilometers, 20, 30, right? So the more my fuel is going to be, or in a lot of cases for different cars, the more the fuel, the more the distance that you can cover. So at the end of the day, when you plot the graph for different cars, you tend to have something like this, for example. Just going to use this as an example. You can see. So it kind of like follows a pattern that we can see through here, and this is more of a positive correlation between our fuel and our distance, so it's generally going in this direction. And for this, all we just need to do is to find a line that will go through it, and we'll just get the line of best fit. And usually that's what the whole linear regression concept is about, to help us to find the best line that will go through this. But in some cases where you just need to do a classification problem, let us say, for example, now, how many people are likely to get their insurance when it comes to their age, when looking at the ages, for example. So let's say I have ages 5, and okay, let me not use 5, let me use 10, 20, 30, 40 to like 60 and 70. Let's say I'm talking about insurance to them now. So I say 0 is for those that are getting no insurance, and I say 1 is for those that will get insurance. So in this kind of case now, what will most likely happen is those that are of the lesser ages, let's say from 10 to like 40 or 0 to 40, you have less of them having you have more of them having no insurance, for example, now. So you tend to have something like this. And with the increase in age, let me just extend this a bit, let's say 80 and 90, right? You tend to have more people that will sign up for your insurance. So we might have a few people that are like this, probably 20 that will get one, 40 that will get one. But you tend to have more people that are in this age bracket that will get an insurance. Okay, and just to make things a bit balanced, you have some older people that will still not get an insurance, to be honest. Okay, so for this kind of problem now, if I draw a line through this now, you can see that this doesn't really do justice to helping us classify whether it's going to be a 0 or a 1. So the best option that I'm going to have is to do something else. So linear regression is bad for these kind of problems. I wouldn't recommend it, or no one would recommend it, to be honest. But what I would do, or what is the best, or what the best solution is in this kind of situation, is when you have 1 and 0, and you have things like this. You have things like this here, and you have things like this here, for example. So the best thing we can do is to have a line that goes like this. So have something like that. So you can see this helps us to give a better prediction to whatever classification problem we have. And in this case, we have the age. Let me just write it: the age and insurance. Insurance. Forgive my handwriting. So this does more justice to the whole thing. So I would say this is far better than this. Trust me, it is far better for classification problems. And what's going on here is for the linear regression, if you remember, is we have things like we have the mx plus c, and that's where the whole formula comes from. But for the logistic regression, we'll still use this, but we're just going to make a few tweaks to it. So we have logistic regression right here, and that will give us 1 over 1 plus e raised to power minus z. So that's what the whole thing's about. And what we're going to do is just to plug this into this right here. Okay, so the formula for logistic regression would tend to look like this. It might look different in other places, but you tend to have something like 1 raised to the power e raised to the power minus. Then you have mx plus c. So if you notice, we just plugged in this guy here and we just put it here. So that's the whole thing about logistic regression. Nothing too complicated about it. So you tend to have, at the end of the day, you have something like this. So this can be used for different kinds of classification. Is this flower iris, you know, the usual iris data sets, problems. It can be used for that. It can be used for cancer problems. It can be used for different things. Just it can be used for number recognition. So it's just a matter of knowing which one to use at the perfect time. Okay, so next up, we're just going to go to the code right away and show you how this logistic regression is a very good application or a solution for our classification problems. Okay, so moving on. Now we've seen how theoretically the logistic regression is better for us in the classification problems. So jumping right into the code, we'll just try to do a simple classification for breast cancer where you have the malignant and you have the benign ones. So just to quickly clear up on that, so we have breast cancer, so we have the malignant versus benign, just for you to see this part here. Okay, so just guys see it. Okay, so we have the benign tumor, we have the malignant tumors. So the benigns are not cancerous, while the malignant are cancerous and can spread to other things, to other places. So basically that's the whole difference between both of them. Alright, so first of all, we're just going to import all our dependencies. Just going to copy and paste that from what I've done previously. Just taking a bit of time. Okay, while that's going on, where I got this from, I got this data set from Kaggle. So if you check Kaggle, you can see different data sets on cancer and you can get different things. So these are the different dimensions or different readings that were gotten or were generated by the person that's uploaded them. So first of all, I'm just gonna make our data equals to pd the read csv, because that's a csv file. That's a csv file and it's named breast cancer .csv. Okay, so let's see if that came in well. So to the head. Okay, so everything looks good from there. Okay, so the first thing we just need to do is just to look at the info and see if there's anything we need to correct or clean. The thing that the truth, like I always say, is cargo data sets are usually clean to a large extent, so there's a very low chance, or there's probably no chance that we might need to do any large cleaning here. So you can see none, no, 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 everything is not null, and they're all in the objects. Oh, okay, this is not the object. They're all in the float type, so those are good. Those are just numbers. So diagnosis and ID are just the things that I need to look at. So ID, don't really think it's necessary because still left. We'll decide on that later. Okay. So just to cross check, is there anything that is? Let's see. Just gonna type it. So the sum. Okay, so you can see none of them are empty, so we are good on that part. We are good on that part. So the next part is just for us to describe the data and get more familiar with it. Nothing too much. Okay, so you can see the mean, the standard deviation, the quantiles, and the max, the average, and the count. Everything looks okay. Everything looks okay so far. And probably when I think we can just ignore this one here. So for things like this, if a person is more into a field, they'll easily be able to know the things that might be outliers and things that are okay and things that are probably not okay. But we'll just leave it like this for now. Everything looks good, to be honest, so it doesn't look too bad. All right, so next up we'll just see the things that we're going to be predicting. And what we're going to be predicting here is the diagnosis. Just going to data. Sorry about that. Column. Sorry. Yeah, that's better. Okay, so we have the columns right here. We have ID, diagnosis, and you have the different things. So this is what we are trying to predict whenever we have each of these readings from a particular person. So like I said, the diagnosis can either be malignant or benign. I think that's how to pronounce it. So you either have malignant or benign, and we'll just get those diagnoses to be the ones that will be predicted. And how the diagnosis is done in this case is that it is labeled as M and B. So if I do, let's see, data.diagnosis. Okay, I think this will look better. Let's see, diagnosis. That's unique. Okay, so we have M and B, as we said. So all we just need to do is to replace this one. It's because once it's in ones and zeros, that's a far better format for us to be able to play with it. Okay. Forgive my slow typing. Almost there. Okay, just gonna copy and paste this part. That'll be faster for us. Okay, so that looks good. And I keep on typing data the wrong way, so forgive me. So data like that. And let me just say data, just to make sure it's all good. diagnosis, value counts. So that helps us to show the values. Okay, so our column now, as you can see, is, okay, let me just show it in a better way here. So let me just do 3. Okay, so we can see our data here. We can see that the diagnosis is either it's 1s or 0s, and that has been replaced for us with this. So that just makes things easier for us to play with it. All right, and just going to quickly drop the column ID. So it didn't bother me, to be honest. So data there, you can see that's gone. Just use 3 here. Okay, so that's all good. We didn't really need it for now. Okay, so for us to plot a graph, just for us to see how the count is and everything, okay, we'll have data, okay, diagnosis. This is just the thing about Matplotlib that we can take. Could take some time for us to get it right. So value counts. Okay, so equals to bar. Okay, forgot to put that in a string format. Okay, so we have kind equals to bar. So let's just see if this will go. So you have something like this. So you can see the zeros are about far more than the ones, which is a good thing. So we can see 357 and our 1 is 212. So that's what's represented here. So just to make things look a little bit more beautiful, I'm just gonna add these lines right here. So X label and count and the rest. So that's all done. Okay, so the next thing we just need to look at is the correlation between the rows that we have. And what I'm just going to do is to use Seaborn, and I'm just going to copy and paste this because of time. I'm trying to make this as short as possible. So we have that. So you can see our correlation. This is more of a correlation matrix in this kind of case. So we have each of the rows, and we can see how much they correlate with each other for here. Okay, so next up, we're just going to filter the data set by that correlation. All right, so doing that. All right. Just to filter our data sets, we have columns right here. Just to do the parts, data, the columns. So we have data, the columns, just similar to what we did here, just to get a list of those columns that are in the data sets. And I'm going to have a threshold, and this threshold is going to be what is the minimum correlation value that it wants to be in the data set. So if it's less than that, then I don't want it. So I know there can be negative correlation, but just to speed things up, so I'm just going to use 0.5 as my threshold in this case. But if you would like to put the negative correlations into consideration, then be my guest. So we have the dropped columns, and I'm just going to put those in a list right here, and then I'm going to make it an empty list. And for any columns or any values that I see that the correlation threshold isn't met, then those are going to be dropped. So basically that's what's going to happen in this case. So let's say for sorry, Okay, so next line, just going to say for, I can't think of an iterative, so I'm just going to use X. That's usually what I'm used to be honest. So I'll just use X. So for X in columns, we have if data dot core. Okay, let's show how it looks like. And I made that mistake again. Okay, so we have something like this, and this is going to help us with filtering out the. So this is going to help us filter out most of the columns that we don't need anymore. Okay, so next thing we're going to do is data.core .loc. So what I'm just trying to say is for each of the columns, if it doesn't meet that threshold, then we want that to be out of the way, basically. So this will be less than COR threshold. Then it wants that to be an X. Okay. It's a filtered course. So we're just going to drop those values that we see that we don't want. Okay, so drops columns, LMS access is equal to 1. Okay, forgot to type that, sorry. So for X in columns, and I made a mistake about my spelling again. Yes, I will say this data is my nemesis in this case because this isn't too many times I've made that spelling mistake. Okay, so moving on, we can see that we have filtered most. Okay, I won't say most, but we've filtered some of it. Sorry about that. So we filtered some rows, and now we can see that, a lot of it has been made to show that there's a good correlation between our diagnosis and the other columns in our data set. Okay, so moving on, I'm going to be quite fast from here on because of time. So I'm trying to make this as short as possible. So first thing first, I'm going to make my X to be the rest of the data set and not the diagnosis column. So I'm just going to drop the diagnosis, and the rest of it is going to be our X, and our Y is going to be the diagnosis column itself because that's going to be our target. All right, now I'm just going to do a scalar on this because you have some of the values that are quite different, to be honest, so we don't want to make our logistic regression model to look very funny. Okay, so next part, the usual train test split. The train test split here. Then we have our logistic regression. So that's going to be our logistic regression object right there. And the next thing we just need to do is so we fit the training data set into here, so we fit it into there. So the next part is just to, sorry, record sounds better. So our Y predict would now be log, let me say wedge dot predicts X, let's say X test, yeah, right. Okay, so the next thing we now need to do is to do a confusion matrix for this one. And what a confusion matrix is, for those that are not familiar with it, is basically just this. So just going to scroll down for a bit. All right. So what our confusion matrix in this case is going to be, it's basically just something that helps us to know how well the model is doing to an extent. Kind of like gives us a visualization of something like that, and helps us know the kind of how well it's predicting some of the values, or all of the values rather. So here, for example, we have this. Just gonna forgive my drawing. Okay, so we have confusion measure like this. It's just a box. So let's say here is going to be my actual, and here's going to be my predicted here. Okay, so we have, this is positive, this is positive, this is negative, this is positive, and this here is negative. Okay, so if something is positive and we predict positive right here, then what we're gonna have is the true positive. So this is gonna be the true positive. And if we predicted something is positive but it was actually negative, then we'll say this is a false positive right here. So say this is a false positive. So if something was negative but it was actually positive, then we'll say this is a false negative. Taking too much time to write. Okay, and if we have a negative and it is actually a negative value, we have our true negative here. So basically this is all the confusion matrix is, and it shows us how well the classification model is predicting some of those values. So this whole concept right here is what we use in the ROC curve. So here you have the true positive rate, and right here you have the false positive rate. So this is usually 1 minus, I think this one should be specificity here, and this one is sensitivity. Okay, so basically that's what these two are right there. And what we need to know about it is that for the ROC curve, it usually looks something like this, but in most cases it never looks like this, but just for theory 6. So it usually looks like, just clean this up so it looks nicer. So over here, so what we, I don't know why that go. So what we usually have here is something like this, and when we plot it, this is our ROC curve goes. So it's usually, we calculate the true positive rates using these values, and we calculate this also using those values. So we're just going to see that in the later part of our code, and usually we have under this, you can see this looks like an enclosed area. We have the area under the curve. So we use all of this to do the ROC and the AUC in summary. All right. So moving on, just going to see if I can close that. Let's see where there's a way for me to close this right here. Sorry about this. Now, what we just need to do is just to plot a few things, and when we plot this, I'm just going to copy and paste this just to make things a bit faster. Okay, so we have the confusion matrix. Remember, this was imported earlier, and that should be from scikit-learn metrics, accuracy score, confusion matrix, and the rest, which you'll see very soon. So the next thing we just need to do is to plot our confusion matrix, and this is what we see. Let me see if I can just make this look a bit neater. Okay, let's show. Probably shouldn't have tried that. Okay, so we have something like this, and you can see our true label and we have our predicted label. So this can be anyways. It can be actual, it can be true, it can be actual on one axis and predicted on another axis. But basically, we just need to know which one's which and be able to interpret it in the right way. So our accuracy score for this model, let's see how well we're doing, is 0.94, which is 94.6%, which is good. That's a good score. And when we see what we have this. So this is quite a good score, to be honest. But this is a very, we don't know the origin of this data set, so we can't say that the model is particularly a perfect model. But in this case and in this context, I mean, it looks good for us. And in the medical field, there are a lot of things that you have to consider, because these are people's lives that are being considered. So there's a lot of things like threshold and the accuracy that are highly considered and are really, what's the word now? They're really put under a microscope, because it won't be good if a person actually has cancer and the person is predicted not to have cancer, and once those kind of things are mispredicted, then you know the kind of implications that can occur. So these things, the hyperparameters, the values and different things can be put under a microscope. But just to make things a bit clear, this is a good score. This is a good score in most cases. But it would have better if we had 0.97 or 98 or something else. But it's still fairly okay. So moving on, we have, just going to, this is a lot because of the matplotlib parts. Forgive me. I'm just going to paste this. And we have our ROC curve. So usually in the textbooks you see that it's like a curve, but in this it's more like a straight line. So trust me, in most cases in the real world data, it doesn't look very pretty as you see in the textbooks. But this is what we have for now. Very okay. It looks like a good ROC curve. I mean, the AUC looks like it's going to be good. You can see the area is 0.94, and usually we want to take a threshold that will be in this region right here. So this region is usually the best in the vertices that we can see there. All right, so basically that's all we have that's all that's involved in the logistic regression cases in most instances. So this particular model that we have helps us to see which person has the higher probability of having cancer, or the malignant cells, or the benign tumors, or the malignant tumors. Forgive me. So it's all about making sure that all of this is good, accuracy is fair, but remember not to be too dependent on this in the real world. But just for the sake of showing how logistic regression model works, this is not too bad. So there are other classification models that we have, which are quite good, but logistic regression is probably one of the simplest and it's quite straightforward. So thank you for sticking with me to the end of this video, and hopefully we shall see each other again very soon. So thank you very much and have a lovely day or evening.